Hi, in this video, we want to take a look at cross-validation. Okay, so remember, when we're doing machine learning, our ultimate goal is to take some predictor variables and predict what our target variable will be in the future. So if I know what the predictor variable is going to be for something that's, let's say I see the predictor variables, and then I'm going to maybe a week from now, a month from now, a year from now, something like that, I want to predict what the target variable is going to be. What I want to do is build a machine learning model to help me see what's going to happen. And we want as best of a prediction as possible. Okay, so here we're going to take some Candy data and we're going to do cross-validation. So cross-validation, the reason why we care about this is, in reality, what I want to know about is the population. I want to know what's going to happen for the population of the population source of my data. I don't actually care about my data. I care about the population that the data is coming from. I have my sample. My sample is my approximation of the population. And what's going to happen is that we have the sample. This is what we build our data on. And this is what we truly want to know about. There's always going to be a disconnect between the two. And I need to have some kind of idea about how good of an approximation is my sample to the actual population. Now, whenever we're doing statistics, if we're doing data science, we're doing machine learning, we honestly don't truly know what's going on. That's why we're working with data. If I knew what was going on, I wouldn't be using math. I would just go and do it. I mean, I wouldn't worry about it. We would just get at it. But when we don't know and we have data, we start using statistics, machine learning, AI systems, stuff like that, to figure out what's going on for us. Okay, so what we're going to do is we're going to try to get an idea of how good our model is going to be at predicting the future. Now, honestly, my experience is that these estimates are going to be optimistic, but this is the best that we can do with the data at hand. Okay, so remember, I fit the model to my data, but I am interested in the population. I need some kind of indicate so I can see how well it fits to the data I built it on. That's not what I'm interested in. So cross-validation is what I'm going to do. I'm going to take the data that I'm going to build my model on, and I'm going to split it up. In this example, we're going to take our data, we're going to split it up into 5 groups. What we're going to do, I've got 5 groups. This group of data, so let's say I have 100 observations. I have 100 observations, I split it into 5 groups. So I have 20 observations in this group, 20 in this group, 20 in this group, 20 in this group, 20 in this group. So I have 20 rows of data here, 20 rows, 20 rows, 20 rows, and 20 rows. Okay, so I've got my 5 different groups. What I'm going to do, this one is going to be my validation set. These 4 are my training set. I'm going to build a model on these 4. I'm going to check to see how accurate is the model on this group over here. Now, once I do that, I move to this set. This set is going to be my validation set, and these 4 are going to be the training data. These 4 are going to be the ones that I build my model on. Move on to the next one. This one is going to be the validation set. I'm not going to wave my middle finger at you. It'd be more interesting of a video if I did though. Now these 4 are going to be the ones I use to build the model on. And then come along. This one is going to be the one that is the validation set. These 4 are going to be the training data. And so here, I'm going to, it's like I'm pulling this one out. These 4, I build the model, then I check to see the model's accuracy on this one. So you'll see that I do this 5 different times. So I'm building 5 different models, and I'm getting the validation accuracy on 5 different sets. Okay, so that gives me a collection of measurements of how accurate my model will be. So I can get an idea of the quality. Why do we do this like repeated aspect? Well, it ends up that if I just do this, like maybe I split my data, and I run this, what can happen is by happenstance, by splitting my data, I can get an unreliable estimate of how accurate it's going to be. By repeating this 5 times, I can be more confident that I have an accurate measurement of how well my model is going to perform in the future. Okay, so this is really the gold standard for evaluating your models at this point. When I first got started in data mining and machine learning, there really wasn't a lot of talk about this. This was like, people knew about it, but people really didn't do it. Now, like, this is the way to do it. Honestly, in about 5 years, someone may come up with a better method. I don't know, maybe, maybe not. But for now, this is the gold standard, and this is the one we want to go with. Now, if I have a very, very large data set, then I probably don't need to do this repeated 5 business stuff. I don't have to do cross-validation. The bigger the data set, the less important it is to do cross-validation. But if I have a smaller data set, then I definitely want to use cross-validation. Okay, so what we're going to do, we're going to take some data, then we're going to do cross-validation manually, and then after we get through with that, we'll go through and we'll have a built-in function in Python do it for us, which is the smart way to do it. Anytime there is a built-in function, we almost always want to use that function. We don't want to do it manually, because there's usually, if a lot of people are using the same function, if there's problems, it gets caught. But if I'm building my own code and there's a mistake in there, the only person who can spot it is me. But if I'm using Python's functions and there's a mistake, people all over the world can spot that mistake and get fixed. Okay, so let's get going. Let's go ahead and get Seaborn in, matplotlib, NumPy, pandas, because that's how we roll. All right, this data set is the Candy Power Ranking data. So the data set comes from from a survey of people clicking which candy they preferred over another in a head-to-head competition. It's posted on Kaggle. I'll go ahead and post this in Canvas. And we can see that we have all these features in the data. For today, we don't really care about the data. We care about the cross-validation, and we don't really care about the modeling technique. So something that is important to understand when we do our modeling, I feel like a good place to start for machine learning really is to understand like the end result and then go backwards. And so you'll notice that when you look at videos about machine learning, people tend, authors and speakers tend to focus on model structure a lot. My opinion is that's not really what's that important. What's important is getting a good model. In the end, I want good predictions. I don't care about anything else. I don't care about the structure. I don't care about the math. I don't care about the data. If I have a good prediction, I'm good. That's what my boss wants. That's all I care about. I don't care how I get a good model. I don't care how I get a good prediction. If I get a good prediction, my boss is happy as a flea in a dog show and everything's good. So I want to emphasize the importance of measuring the quality of our model over the structure of our model. All right, so let's go ahead and read the data. So it's listed in a CSV format. So we'll go ahead and pull that in. Now we're going to manually perform cross-validation. So this isn't how we do it. So in real life, do not copy this section of code. Go a little bit lower in the code to do it. But I want you to see how we manually do this. So first thing we're going to do from sklearn, we're going to go ahead and get k-fold. K-fold is how I'm going to split the data into the 5 data sets. All right, so now I'm using the k-fold function. And you can see that I'm saying that I want 5 splits. I'm telling Python to go ahead and shuffle the data. Shuffling the data will slow things down. If I'm not worried, if let's say my data came to me like already like sorted, then I might want to shuffle things to make sure, I will want to shuffle things to make sure that I have an even distribution of items. And then we need to go ahead and put a random seed generator number. We do this for reproducibility so that down the road, I could do this again and get the same results. Now, something about reproducibility is that if I use a different operating system, a different addition, So if I'm using, Python 3.2 and you're using Python 2.1, we cannot expect to get the same output when we do, when we set the seed, especially if I'm on like a Windows machine and you're on a Mac. There's going to be differences, but a lot of times we'll be able to reproduce it nonetheless. Okay, so now I've already got the candy data loaded, and now I need to get my predictors and I need to get my target variables split up, because that's how Python works. So I'm going to have X as the predictors, Y as the target variable. And here we can see that we've got chocolate, fruity, caramel, peanut, almond, nougat, crispy, hard, bar, sugar percentage. We got a bunch of them. And Y is the winning percentage. So this is going to be a regression problem. So we've got values from 0 to 100, where what we want to do, we want to take the features of the predictors, and we want to be able to predict what percentage would be able to win in a competition. So let's say, next year, we're a candy manufacturer, and we want to make sure we get the best candy possible. So we could use this model to try and figure out what, if we make a new candy, what percent of the time will it be favored over other candies? And so that way we can make more money because we have the best candy on the planet. All right, so now what we're going to do, we're going to split up our data. We're using the k-fold function, and we're going to apply it to the X data set. So let's take a look at what it splits. All right, so what this is going to do, this is going to generate indices to break up the data. So it's going to say, it's not going to actually split up the data. It's going to say which row goes into which of the 5 sets. And so when I say, let's say row 20 goes to subset 3, both the X and the Y for that row go into that subset. All right, so now what we're going to do, we're going to build a random forest. Oh, hello. Random forest is like my go-to whenever I'm doing spreadsheet problems. For very little work, you get a very accurate model. It performs pretty well when you have like moderate or larger data sets. It's usually not the best that you can get if you have big data, but for the amount of effort, the amount of time you have to spend on it, it does a really good good job at things. So random forest, what we're going to do, what random forest does, it randomly picks rows of data, a subset from the training data, and it randomly picks predictor variables on each step, and it makes a decision tree. So it makes a whole bunch of decision trees. Well, we have a collection of decision trees. A collection of trees is called a forest. And that's why it's called a random forest. And because of this random selection, it's random. And that's how it works out. So let's go ahead and do that. So let's go ahead and get from sklearn ensemble. And why is it called ensemble? All right, so in this situation, let's say I make 25 decision trees with this random sub-selection algorithm. Well, ensemble means I'm bringing all those models together into one like big overall model. And so that's why it's in the sklearn ensemble. All right, now metrics, we need some way to measure the quality of our model. And I'm going to choose mean squared error for now. Usually, so if you're taking classical statistics, like classical linear regression, you're probably most familiar with mean squared error. That has, this has a lot of good algebraic and theoretical properties when we're doing linear regression. So this gets emphasized a lot. My experience personally is that mean absolute error is actually better for the purpose of real world problems, but mean squared error is definitely one that's well received and well accepted. All right, so what we're going to do, I'm going to make a random forest regression model. We're going to make 25 decision trees by randomly selecting subsets of our rows and subsets of our columns, so subsets of the observations, subsets of the predictor variables, and to make it so that we can get the same output later down the road, I'm going to go ahead and put in random state of 823. 823 is UCF on a telephone, by the way. All right, so now let's go ahead and run through this. Now remember, I'm doing cross-validation manually, so this is not how I'd actually do it in real life. I want you just to see what we're doing. So what's going to happen is that splits, which we generated with the k-fold function on X, that's going to give us the indices of which row or which observation goes into which of the 5 subsets. Then what we're going to do, we're going to grab that subset, and that's going to be our training data. So here, X train, Y train is we're going to drop those indices into our data, and we're going to grab just those rows. So this is going to, so remember, since I'm breaking up into 5, this part is going to have 80% of my data. And so, 4/5. Here, it's going to be 1/5 of our data, 25% of our data. That's what we're going to use to validate our model, to check to see how accurate does it look like this model will be. All right, so now at that point, I have my training set and I have my validation set. My training set, I drop into the random forest model and I fit it right here. So now I have the model, it's built. I need to check to see how accurate is it going to be. So I'm going to go ahead and run predictions on the predictors in the validation set. And then I'm going to check and see, I'm going to take the Y validation set. I'm going to take the predictions from the X validation set, and I'm going to drop that into the mean squared error. And that's going to give me a measurement of how accurate my model is. I want the smallest value possible. All right, so I went ahead and ran it, and we can see that we're getting as low as 90, so that's the mean squared error. So that's the average. So I take the error, take prediction minus the observed in the validation set, subtract, square it, then take the average of those squares. So my smallest one is 90. My largest is about 213. So I can see that the values are going from 90 to 213. I mean, if you think about that, that's a pretty big spread. So if I would have done this on my own, like only one time, I might have gotten that 90. And if I would have gotten to 90, I would have thought, wow, this is a really good model. Well, another iteration, I would have had double that. And so what if I get like a really, really big number, just like randomly, when I go through this, through a regular non-cross validation process, I could get like a really big number, and I could skip over a very good model. If I could a very small number, I could think, hey, I have a better model than I really have. The cross-validation, what it does, I can average out all the mean squared errors, and it gives me a better idea of the actual predictive value of the model. So taking the average almost always will improve our estimate. So, here you can see that by the random picking, if I would have just by happenstance gotten the 90 or the 214, I'd have a very different impression of my model. 213 is more than double what the smallest value is. I mean, it's kind of a big gap. Not kind of, it is. All right, so now let's go ahead and let's do this the smart way. Let's have Python do all the work for us, and let's see what happens. All right, so what I want to do from sklearn, we want to pull cross-val score. We want cross-val score to be pulled in. So go ahead and import it. Now, the default for regression is going to be either R or R squared, which usually isn't the best way to go. I find that mean absolute error is the best way to go for regression models in real life. Because if I'm doing like the mean squared error, then when I explain to someone without a stronger statistic background, like, why are you squaring it? Like you know, they don't really care what's the squared error. They want to know if I'm talking about predictions, how reliable is it going to be? They're not going to want the squared value. They want the absolute deviation, which is the MAE. So I find that this is received better by those without you know, statistics background. The mean squared error has a lot more properties from a theory point of view. It's much easier to work with, you know, because absolute values just aren't as algebraically as nice as squaring. But I strongly recommend that you use MAE whenever possible. Okay, so now what we need to do, I need to pull in that mean absolute error because I feel like that's the better measurement. Now, if I'm going to be building multiple models, I want to use the same metric to compare them throughout. So far, we haven't really touched on multiple model building yet. So I need mean absolute error and make scorer pulled from sklearn metrics. And now I've built a scorer with mean absolute error. So we're looking good. So now let's go ahead and generate the cross-validation. So I'm going to take cross-val score. My estimator is that regression model that I already built. Notice that I'm not splitting up the data myself at all. I'm not doing any indices. I'm not doing k-fold. I'm dropping the entire training set into cross-val score. So here I've got the X. Here I've got the Y. Here I specify how many subsets do I want to split it up into. And I specify how I want to evaluate model quality. Go ahead and run it. Now let's go ahead and print that. Let's take a look. Okay, so here, the first thing I want you to notice is that these are very different numbers. Why are they different numbers? Well, remember that squaring is going to make a number bigger than 1 a lot bigger. So, you know, it's just a completely different scale. But here, it's easier to interpret what does it mean. So here, on average, the predictions were off by 11% on average. Here, on this run, the predictions were off by 7%. Here, off by 6, 13, and 9. So it's easier to interpret when I use mean absolute error. And here's the average. So I can see across all 5 of them, it looks like it was off about, you know, on average by about 9%. And then the standard deviation is about 2.5. So if I wanted to get an idea of how far out a range of values I could expect to have down the road, you know, because I have an average and standard deviation, I can, you know, predict like what's the likelihood that it's going to be like this much, this big or bigger if I really want to. Well, that's cross-validation. This is a critical component of machine learning. This is super important. If you're looking at a whole bunch of different like machine learning topics, make sure, like, honestly, learn about evaluating a model before you learn about models. Honestly, like, get that in your head that the most important thing is the quality of my predictions. If I don't have quality predictions, all the other aspects of machine learning, data mining are stupid and pointless. Make sure that you are solid on model evaluation and model comparison. Take care and have a great day.